This lecture will serve as a signature lecture in Engineering 17. This is probably one of the most important lectures. We are going to cover nodal analysis, and we're going to focus first on circuits that have no voltage sources. This is when you add voltage sources, we'll learn later how to treat that in a different lecture. But the bulk of the method essentially will be covered here in terms of circuits without voltage sources. So this is a significantly important lecture because nodal analysis is the most important circuit analysis method we have. So let's start this discussion here by sharing screen and talking about circuit analysis in general. So obviously, circuit analysis is the essence of this course. So that's it. It's in fact, it's in the title of the course. And when we talk about analysis, circuit analysis, we generally talking about either calculating voltage and or current. Generally, we don't do both. We do either one for circuit through or across circuit element, and we do so via some established process or some established procedure. So far, we've covered a number of laws. We've covered some pieces of methods. We've looked at Kirchhoff current law, Kirchhoff voltage law. We introduced the resistor, Ohm's law, and then we talk about current and voltage division as well. So we're going to develop two highly structured circuit analysis methods. The first one is the most powerful. It's called nodal analysis. And then the second one we'll do later in the course is called mesh analysis. So our focus today, again, is nodal analysis, but only for circuits that have no voltage sources. So I'm going to do two examples today, one of them on PowerPoint, one I want to do on paper so that you can see the thought process, and I'll jot notes because I want to mimic to you the way I want you to solve these problems, and then I'm going to have you do one and then cover the solution after. So that will be the essence of this lecture today. So in nodal analysis, we essentially put together Kirchhoff current law, Kirchhoff voltage law, and Ohm's law into a structured process. Okay, and the structured process is designed to calculate the voltages across element. More specifically, we're going to calculate the so-called node voltages. They are the variables. They are the unknown in that method. So when we look at nodal analysis, the first thing that should come to your mind is that we are calculating voltages across element. So if you think about your car battery and you think about the red and the black pole, so we can look at the voltage, the 12 volt across by the voltage at the red minus the voltage at the black. Okay, that's the 12 volt is the potential difference, the voltage difference across the two nodes. Generally speaking, we're going to come up with n equations for an unknown, 2 equations to unknown, 3 equations to unknown. I will not assign you a circuit that has more than 5 nodes. That's probably because beyond that, it becomes more just laborious. It doesn't really provide any insight into the solution. So that's pretty much, we'll try to restrict ourselves to that. Okay. So again, our focus today is circuits with no voltage sources. I'm going to describe a method. The method, of course, you'll hear me, but it'll make more sense when you see a circuit that I'm applying the method to. I will also send you an announcement structured so that you can have that more specifically on paper. But when we do circuits, it'll become more natural to you. And as you do 5 or 10 circuits using nodal, it'll become pretty much second nature to you. So the first thing when you get a circuit, for me, and you are being asked or you choose to use nodal analysis to solve the circuit, you're going to identify all the nodes in the circuit. Okay, that's the first thing. Again, we're dealing with a circuit that has no voltage sources. So the first thing I'm going to ask you typically when you get a circuit, how many nodes we got? You need to find the exact number of nodes and where they are. Okay, so I'll ask you how many nodes. You're going to tell me 2, 3, 4, 5. And then the next question I'm going to ask you later on, it is how many unknowns we have in the circuit, and you'll know what I mean. Okay, so the first thing is to identify the nodes in the circuit. Then you will select an arbitrary reference node. Okay, it really doesn't matter. And I'm going to have you put this symbol on the reference node. Sometimes I will use that symbol as well, the triangle, in the reference node. Either one will serve as symbol for the reference node. When we select the reference node, in essence, we are saying at that point, we are saying the voltage is 0. Remember voltage, just like we talk about potential energy in the water analogy, that current is like water. In terms of when you raise water above with gravity, you have water essentially pressure force the water to flow. Similar with current, the voltage is the potential energy. The voltage is what makes the current go. So it's the voltage difference that matter, not voltage at a particular point. Okay, so we're going to select an arbitrary reference node. And in our mind, because it's easy, we're going to assign the voltage 0 at that point. So we're going to say that the reference node has a known voltage, and it is 0. Next, we're going to label the other nodes. Of course, if we have n nodes, we're going to label the n-1 nodes because one of the nodes is going to be the reference node. We're going to label them V1, V2, V3, and so on. They are going to be unknown in the problem. Okay, these are what we call the node voltages. They are going to be unknown. Please make sure you don't duplicate labels. If for some arbitrary reason V1 or V2 was used inside the problem, please make sure you don't duplicate that in the node voltages as well. Next, we assign current. And when we assign current, we're talking assigning current label and arrows because there is no such thing just current without the two of them. We assign current arrows and label, and we're going to call them I1, just that sequentially. Just make sure you don't duplicate current. That's essentially what I'm asking you to do. And we're going to assign current to passive elements, namely resistors. That's the only passive element we have, assuming there is no current on that resistor. If there is already a current, use that current. Okay, so we're going to assign current on resistors that have no currents. So at this point here, right here, I'm going to say we have prepared the circuit for solution. We've done essentially all the preparation we need, and we can start writing the mathematical solution for solving the circuit. So the major step in that mathematical solution is to write a Kirchhoff current law equation at each node that's not the reference node. So remember what I say, if you have n nodes, I'm going to ask you how many nodes you have. You're going to tell me whatever the number n is, whatever the number of nodes. Then I'm going to ask you how many unknowns you got. You're going to tell me n-1 unknown. So you're going to write essentially a Kirchhoff current law at each node that's not the reference node. That's going to generate n-1 equations in terms of current. I expect you to write these Kirchhoff current law equations in terms of current. I will grade you based on that you write them in terms of current. Okay. Then I want you to step aside and write Ohm's law for each current that's on a resistor. And you're going to write these currents in terms of these node voltages. I'm going to show you how to do that. So that step essentially that you're seeing, that second step on the PowerPoint here, allows you to go from current to node voltages, which are the unknown you have. So you're going to write all of the currents in terms of the node voltages. And when you do this, the passive sign convention is essential. All right. We're going to then take those Ohm's law equations. We're going to use them into the KCL equations. We're going to use them into the KCL equations, and then we collect terms. If we do things correctly, we should have a set of n-1 equations for the n-1 node voltages that we have. Okay. That's the essence of the method. Of course, unless you practice, you don't see it, and we're about to do that today to get you basically on your way. Okay, so let's look at the first simple problem here. It's asking you to calculate the voltage drop, the potential drop across each element. You can put your plus and minus however you want. It doesn't really matter here. It's just for us to start getting the hang on using the nodal procedure for circuit with no voltage sources. Okay, so I'm going to do this problem on PowerPoint. The next one I'll go on paper and do it with you. Okay, so that's a circuit we have here. So what are the preparation steps? Identify the node. So I'm going to see there is one node here. Again, anytime you have a wire, you have a node. So this is all one node, just like I'm showing you right here. Okay. Anytime you own a wire, it's one node. Until you're comfortable with it, feel free to do what I'm doing here. Okay. There is another node here. Anytime I'm on a wire, as long as I'm touching an element, I have one node. That's one node. Okay. And here, there is another node. Again, anytime I'm on a wire, I have a node. So I have 3 nodes in the problem. Okay. So I'm going to show you essentially the next one. You see, I select the reference node at the bottom. I put the reference node at the bottom. And I label the other 2 nodes on top, V1, V2. Please know that the reference node selection has no bearing on the solution correctness. No bearing at all. You can pick any node as a reference node. There is no, you better not do this or that. Any node, it's totally arbitrary. So at this point, you should recognize the 2 unknowns you got are V1 and V2. So 2 unknowns, you need 2 equations. Where are these 2 equations going to come from? They're going to come from writing a KCL equation here at node V1 and writing a KCL equation here at node V2. That's where the 2 equations are going to come from. So let's do that. Let's write a KCL equation at node V1. But before we do that, of course, we have to put currents on this element on the resistors. Remember, I told you one of the steps is to put currents on the resistors. I put the direction of the currents totally up to you. I could put I2 coming down the way I put I2 or going up. It doesn't matter. Now, once I put the current, you're going to see put these plus and minus. These are training wheels. These are training wheels for you. Eventually, I'm not going to put them again. This is to remind you, once you set the current direction, that essentially set the voltage across the resistor because of the passive sign convention. So I'm putting the plus and minus to help you. We'll drop that very shortly. Okay. So the currents are arbitrary. I could have put I5 the way I have I5 going left to right. I could put them essentially going right to left. It doesn't make any difference to the solution. Okay. Now I'm in a position to write KCL equations. So generally, I write my KCL equations, or I write all of them at once, and then I go ahead and do Ohm's law. Because I want to show you the entire process for the node V1, so I'm going to do KCL and then Ohm's law, put them in there so that you see how that works. Okay. So I'm looking at KCL at node V1. Okay. Current coming in equal current coming out. What's coming in? 4 amps is coming in, 4 coming in. What's leaving? I2 and I5 leaving. Okay, so my equation becomes 4 equal I2 plus I5. I often recommend students, when they write the KCL, to look at the surrounding of the nodes and count how many leads that connects to the node. You just want to have 1 term per lead so that you're not missing a current. Because sometimes the nodes are quite spread out. So you just want to take a moment, just count how many leads you have that's connected to that node. Okay, that's probably a wise. Then we write Ohm's law. Again, I typically do all my KCL first, then do Ohm's law, but I want to show you the process completely for that equations. So I'm going to write Ohm's law for I2, and I'm going to write Ohm's law for I5. So for I2, Ohm's law is where the plus is, and that's why I put those training wheels plus and minus for you. Where the plus is, which is where the current enters. So V1 minus where the minus is, which is 0, the reference node divided by 2. So it's V1 over 2. Similarly, I5 is where the plus is, which is V1 minus V2 divided by 1. Okay. So I'm going to take these 2 and I'm going to put them into the KCL equation. Okay. So when I do that, it's going to be 4 equal V1 divided by 2 plus V1 minus V2. I'm just going to put these 2 Ohm's law equation into a KCL, and then typically you're going to do common denominator and then collect terms. So that's what I do in this slide here. This is putting the Ohm's law into the KCL equations. And then typically what I would do is multiply that equation by 2 to make it easy to collect term, but I just essentially add all of the term for V1. That's why you have the 3/2 V1 here. So that is my first equation for my two unknowns. First equation for my two unknowns. That process is central to this method, to nodal analysis. If you get what I just did here, the KCL equation, how I prepare the circuit, Ohm's law, put it in, collect terms, you're essentially on your way. I'm going to repeat that process, the same process at node V2. So let's do that. So at node V2, I look at what current's coming in, what's current coming out. Current coming in is I5. I5 is coming in, and what's leaving? I1 is leaving, and -6 amp is leaving. So that's why you see my KCL equation right there. -6 plus I1 equal I5. Then I do Ohm's law. I've already done Ohm's law for I5. I5 is already done. It's V1 minus V2. Then I can do Ohm's law for I1, and Ohm's law for I1 is V2 minus the reference node voltage, which is 0/3. So I put that, both the equation for I5 and for I1 into the KCL, and I get this equation here. Okay. Again, typically I would multiply by 3 to get into the same denominator, but it's so easy. I just combine the term for V2, and I get my second equation for my two unknowns. So I have two equations, two unknown at this point. All right. This is where I expect you to basically use your calculator. Okay. If you haven't figured out how to use your calculator to linear set of equations, solution of linear equations, please find out how to do that, because that's going to be I'm expecting you to do that. I'm expecting you to be very comfortable doing this. Okay. So we solve for the node voltages, V1, which is 1133, and then V2 is 13 volt. Mm-hmm. So once we have the node voltages, we can answer the voltages across each element, given the way I position plus and minus on these elements. Okay, so the problem is fairly done. That was a simple question here, but it exemplified the method for you for nodal analysis. Okay, so I'm going to do a second method, but I'm going to go on paper and do it. I'll say to you that if you look at my notes, my PowerPoint notes, you will see that there is a section on Cramer's rule. You are not expected to know Cramer's rule. I'm leaving it in the notes because it's kind of almost a historical content that I think it's interesting, and you might be aware of it. You might want to be aware of it, but you are expected to use your calculator to solve this system of equations. Okay, so I am going to pause right now and bring in the second problem. So here's the second problem. It's asking you to find the node voltages for this circuit. Remember, in this course, you will get a circuit you haven't seen and asked to solve a circuit using either nodal analysis and later on using mesh analysis. Either one of those will be, you're expected to be proficient in both of those. Finding the node voltages. One thing that I point out here, I almost never do this, but in this particular problem here, I'm giving you Siemens values, which are the admittance values for the resistors. So they're essentially 1 over the resistance. It's just to make the math easier. So in essence here, for this resistor here, which is 2 Siemens, that means it's 0.5 ohms. Okay. So this one, which is 4 Siemens, is 0.25. But generally speaking, you're going to have resistance values. Okay. But that's just total moment. So I'm going to pause here. Then I'm going to go to the document camera, and then I'm going to solve this problem so that you see my thought process and you see me doing it on paper as opposed to using PowerPoint. Okay, let me just pause for a second. Okay, so I'm hoping you are seeing my document camera, and then I'm going to doodle the response so that you can see how on paper. So I reproduce the problem here. And of course, the problem is asking to find the node voltages. So first thing I'm going to do here, essentially, the main statement here, I'll try to write the main step that I expect you to do, one of them. And one of them is identify the nodes. Identify the nodes. Okay. That's one of the first step that I'm having you do? Okay, so I'm hoping you're finally seeing my document camera. I had a little bit of a snafu here. The document camera crash, which is going to happen once in a while. So the first thing that I want, and I'm going to put some steps for you to essentially do when you're solving this circuit. And one of the first major step is to prepare the circuit for solution. Okay, so prepare the circuit for solution. And the first step in that is to identify the nodes. So I'm going to do that here using a little bit of color here. So there is a node. There is one node. There is one node here. You can see my red here. I'm doing that on purpose. There is another node here. And there is one node here. Again, whenever you're on a wire, as long as you are not jumping an element, then you have a node here. So I've identified the node. The next step essentially is to select an arbitrary reference node. I'm going to put the reference right here. Okay. That means the node here is 0. The reference at that particular node is 0. The next step is to label the order nodes. And we're going to label them here, V1, V2, V3. So V1, V2, and V3, they are the unknowns. So we have 3 unknowns in this problem, V1, V2, and V3. Okay. So that's the first first step here. Finally is insert currents on our passive elements, the resistors, if they don't have a current, obviously. Okay. So insert current on our passive elements. So I'm going to put I1 going this way. I'm going to put I2 going this way. I3 and I4. Okay. So I've inserted current. I've inserted current on my passive element here. I have I1, I2, I3, and I4. So at this point here, I would say I have prepared the circuit for solutions. Okay. Then now the next major step here is KCL at each node. Except the reference. So KCL at node V1. Current coming in equal current coming out. So what's coming in? I have I2 coming in, and that's equals 6 plus I1. That's equation 1. KCL at node V2. Current coming in equal current coming out. I got I1 plus 8 equal I4. That's equation number 2. Okay. Remember that I have 3 unknowns. That means I need 3 equations. And then finally, KCL at node V3. So what do we have here? We have all coming out. So we have I2 plus I3 plus 8 equals 0. That's equation number 3. Major step right there. Okay. KCL at each node except the reference node. Okay. Then the next major step is to write Ohm's law for each resistor. So in the case of I1, you got, again, remember I have admittances here. So the admittance Y is 1 over resistance. Okay. So remember that. So when we say I1 is V1 minus V2, the minute that I have the current here, I should, in my mind, see the plus minus sign that way. Okay, even though I'm not putting the plus or minus sign, but you should see the passive sign converted. I1 is V1 minus V2 divided by the resistance, which is multiplied by 4. Because again, we're talking about the admittance is 1 over the resistance. So that's I1. I2 is V3 minus V1 divided by the resistance, which is multiplied by the admittance, which is 1. Okay. We have I3 is V3 minus 0 divided by the resistance, which is multiplied by 6. I4, which is V2 minus 0 divided by the resistance or multiplied by 2. Okay. I think I have all of my currents here. All right. So these are the Ohm's law equations. So I'm going to look at your work in that kind of fold, looking at the KCL equation. Have you prepared the circuit correctly? Now, all I'm going to do is essentially use these Ohm's law equations into the KCL equations. So equation 1 becomes I2, which is V3 minus V1, equals 6 plus I1 plus V1 minus V2. Okay. So I can sense everything one side, keeping 6 on one side, and then sense. So what do I have? I have minus 2V1 plus V2 plus V3 equals 6. So my first equation is done, if I did things correctly. Okay. First equation for 3 unknown. Equation number 2, I1, V1 minus V2 times 4 plus 8 equal I4. V2 times 2. Okay. So that becomes 4V1 minus 4V2 plus 8 equal 2V2. So what do we have here? We got minus 4V1 plus 6V2 equal 8. That's my second equation for my 3 unknown. Okay. Finally, equation number 3, right there, which is I2, V3 minus V1, plus I3, plus 6V3, plus 8, equals 0. So what do I have here? I have minus V1 plus 7V3 equal minus 8. These are my 3 equations for my 3 unknowns. This process that I'm describing to you will be how I grade your work. And if you get to the 3 equations to unknown correctly, you will get 75 to 80% of the score for that problem. Okay, having done the process in this organized fashion that I'm showing to you. Okay, so I'm going to go now to the PowerPoint so that I can resume to show you the solutions on this. Let me just pause for a second. So let me just go back let me just go back to that correct one mistake here, and I'm going to say there's a mistake in equation one here. Look at equation one here. I2 is equal to 6 plus I1. So I2 here is V3 minus V1 is equal to 6, and I1 and I1, I'm sorry, 6 plus I1, so it is times 4. Okay, so there is a mistake here, and so this equation is incorrect here. So when I do that here, what do we have? We have 4I1, so this is minus 5I1. Minus 5V1, sorry, minus 5 because 4V1 here, send on the other side, minus 5, and this is plus 4V2, okay? Plus 4V2 plus V3 equals 6. So now these equations are correct here. So we got minus 5V1 plus 4V2 plus V3 equals 6. So now I'm going to go to the computer essentially and show you the solution, and then we'll proceed from there. So this is a solution essentially. If you look at these are the three equations, three unknown, I expect you to be able to put it into a matrix form. I can help you on that. And essentially, when you put into a matrix form, you're just putting the coefficients of the equations. You see the 5, the minus 4, and the minus 1. You're basically looking at multiplying a row of this matrix by the column vector equal minus 6. Again, I can work you offline and we can do a little bit of tutoring on that if you want, how to go from the three equations, three unknown, into a matrix format so that you can put it into your calculator. Okay. Just to show you the answers. So V1 is minus 0.826, V2 is 0.783, and V3 is minus 1.261. Okay, so these are the node voltages. You were not asked for the current. I just happened to calculate the current, but you were not asked the current. So that essentially is the second problem. I wanted to do it on paper to give you an idea of the process here. Now I'm going to step back in here and give you a problem to do, and then I'll come back and solve it. So let me again find the problem for you. Here it is. Okay. So what I want to do here is essentially let you write that problem solution down. And I want you to pause the video or stop the video and go spend about 25 minutes to essentially set up this problem. I'm asking you here to calculate the power, but for this particular exercise, you can do the power later. Let's focus on finding the node voltages. And I'm going to be putting, just so that we have this, I'm going to put the reference node right here, okay? So that we have the same format of a problem. Let's put the reference on the same place. So again, just focus on finding the node voltages, at the very least being able to come up with n equations n unknown using the process that I just described. Okay, so I'm asking you to stop the video and then we'll pick it up on the other side in a few minutes. So, okay, I hope you spend a good at least 25 to 30 minutes working on this. Again, the problem is asking to calculate power for each element. But for this particular exercise, we're going to focus on calculate the node voltages. Okay, we're going to calculate the node. We're going to prepare the circuit. First thing we're going to do, prepare the circuit. And what do I mean by preparing circuit? Identify the nodes. Identify all nodes. Select an arbitrary reference node. label the order nodes. Okay. Insert current on each passive element with no current. Okay. So that's what we're talking about here. So what are the nodes here? There is a node. There is one node. There is one node. There is one node. And there is one node. Okay. So how many nodes I got? I got 1, 2, 3, 4. I'm going to put this node as the reference node. And then we're going to label these nodes. V1, V2, V3. So 3 unknowns. I need 3 equations. Okay. So again, insert current here, I1, I2, I3, totally arbitrary, I6, I5, and I4. Totally arbitrary the direction of the current. Okay, but once you put the current, that determines where the plus and minus signs are on these resistors. Okay, so KCL equations. That's the next major step. So KCL at node V1. Current coming in equal current coming out. So 5 is coming in equal to I1 plus I6 plus I3. That's equation 1. KCL at node V2. What's current coming in and what's current coming out? I get 10 coming in, I6 coming in, and I have I2 leaving plus I5. Equation number 2. And then KCL at node V3. What's coming in? I got I3 plus I5 coming in, and then I4 leaving. That's equation number 3. That's the second major step. The first mathematical step, but the second step, the first being preparing the circuit for solution. Then we go ahead and write Ohm's law. So what do I have here? I1 is V1 over 1. I2 is V2 minus 0 over 10. I3 is V1 minus V3 over 5. I4 is V3 over 4. I5 is V2 minus V3 over 3. And finally, I6 is V1 minus V2 over 2. Okay. These are the Ohm's law equations. Now I'm going to put these Ohm's law equations into the KCL equations. Okay. And I'm going to end up with 3 equations, 3 unknowns. So for example, here, let's work on equation 1. I get 5 equal I1 V1 plus I6 plus V1 minus V2 over 2 plus I3 plus V1 minus V3 over 5. Okay. So that's the first equation once I put the Ohm's law. I can actually multiply the entire equation by 10 to get rid of the denominator. So what do I get? I get 50 equal 10V1 plus 5V1 minus 5V2 plus 2V1 minus 2V3. And then I collect terms. What did that give me? 50 equal, I got 10 plus 5, that's 15, so 17V1 minus 5V2 minus 2V3. First equation for my 3 unknown. If I did my math correctly. Okay. If I do the second equations, what do we have? We have 10 plus I6 plus V1 minus V2 over 2 equal I2, V2 over 10 plus I5 plus V2 minus V3 over 3. Okay. I can multiply this entire equation by 30, and that will get rid of the denominator. Okay. So that gives me what? That gives me 300 equal, 300 plus 15V1 minus 15V2 equal 3V2 plus 10V2 minus 10V3. Okay. Again, if I did my math correctly here, that gives me what? This thing becomes 300 equal. I can send everything on the other side. So I get minus 15V1, 15. This is 28V2 minus 10V3. If I did my math correctly, that's what we get. Okay. Again, finally, equation number 3, I3, V1 minus V3 over 5 plus I5, V2 minus V3 over 3 equal I4 equal V3 over 4. Okay. And I can probably multiply by 60. If I multiply the whole thing by 60, multiply the whole thing by 60, what do I get? I get 12V1 minus 12V3 plus 20V2 minus 20V3 equals 15V3. So that gives me 12V1 and plus 20V2. Bring that here. So what do we have? This is minus 32. So minus 47V3 equals 0. If I did my math correctly. Okay. So this gives you an idea of the process, and I will grade you on each of those steps. The main thing in the Ohm's law here is the passive sign convention. And these two equations, writing them are fundamental. Doing the math after that is a different. So I'm going to grade these two higher than I grade the math, putting Ohm's law into the KCL and collecting terms. I'm hoping I'm showing you the process so that you see how it's done here. So again, let me just show you quickly the answer if I did my things correctly here. Let me just show you. So if I did my math correctly, and it looks like I may have, because I was paying attention, essentially. Okay. Looks like I did okay. So the end result here, so those are the three equations for unknown, and this is the solution for the voltages, the node voltages for this particular circuit, okay? And once you have the voltages, you can calculate power for the resistor. And I'm gonna leave that a little bit for another discussion, basically. That's probably enough for this lecture.